Hey there, those 232 folks. Hopefully you're doing well. I'm hoping that now that we've done the SOS 232 workshop and had a little conversation that went down, you're feeling a little bit better about this class. Again, fully understand as we jump from one variable to two variables in module 4, things got very complicated very quickly. And that's okay because good challenge doesn't hurt anyone. But don't think that you can't do it. I know that it becomes a lot more sort of all over the place, but make sure as you're going through module 5, which also has a lot of concepts to cover and go through the rules of writing worksheet I provided, the additional problem I provided, and realize that we're going to talk a lot for this lecture, for this module. And it's going to come down to just a few additional lines when we write up our analyses. Those lines are exceptionally vital because they make it, one, more accessible to individuals through these visuals we're going to add into it, and two, put up a level of statistical rigor that individuals who are professionals in the statistical sciences, as well as like very higher level social science researchers, will look at your data and really start thinking of what you're writing as closer to fact that will help push toward knowledge, new policy, and so on. So, as we get started, we're going to go ahead and we're going to talk about these sort of differences and explain where everything's about to go. You ready? Let's get the ball rolling. We're going to start out by analyzing relationships and comparing categories with what we know as chi-square. And chi-square is a term we may have not heard before. Don't worry, that's where we're going to introduce this module. In this PowerPoint presentation, we're going to go and continue to explore relationships between two variables through the crosstab data or contingency tables that we've been talking about. And we're also going to provide a new graph called the stacked 100% bar plot. We're also going to begin to formalize what it means to have statistical evidence that a relationship may exist between two variables as we formulate our hypotheses beyond the ideal of practical differences. Again, this module is going to be a bit concept heavy, kind of like module 4. So be sure to get started early, give yourself enough time to pace, and after last module's workshop, remind yourself, you got this. And maybe a lot. Go to the cheat code material to feel comfortable with everything as you get going. Now, we're to start off this lecture as sort of a brief crash course review on bivariate statistics and make sure you all are ready to roll when we start talking about this test of significance again with practical significance. First, talking about the percent difference rule, but then enhancing that with something called the stacked 100% bar graphs. They give a graphical representation of what we see. The chi-squared test is now the new test of statistical significance that we're going to then add another level, up the professional game, and really start to hone in on establishing that we know what we're talking about when we start seeing that relationships exist from a statistical and practical standpoint. Definition, running crosstabs with chi-square, interpreting and writing these things up are the name of the game as we finish up this module. So I'm going to talk about a lot of old stuff very quickly, and I'm going to do it quickly. So feel free to put me on 1.5 speed. It's things you've already heard for the most part, but don't feel too bad if you want to have a quick refresher to make sure that, oh, now I've seen this again. I feel comfortable about this in module 4. So two variables, x and y, are associated or related if the value of one variable gives you information about the value of another variable. And for the rest of the course, as we said before, we're going to compare groups and determine whether an association exists by comparing their descriptive values to see if notable differences are actually there. we're often going to look at whether changes in responses for one variable, like going from folks' graduate degree to ones with less than high school completed, changes the breakdown of a response of another variable, like percentages of not too happy. And before we're doing a bivariate test, we're going to set up our propositions. And it's a good reminder, propositions are basically a clear objective statement concerning our relationships between these two variables. So like, does perceived happiness relate to education level? These associations work in reverse too, which are really cool. I can also say in reverse that happiness is associated with how education levels vary, just as much as I say education levels are associated with how happiness levels vary. If we have causation, and this is module 4 stuff we talked about, a cause and effect, we may not be able to go in reverse. We don't have to worry about that. One of the things that does kind of give us a little bit of breathing room is that everything what we are actually pulling in this course comes from survey data or observational studies that are really more about just picking up the data and looking at stuff. We'll talk about experiments a little bit in module 6. But for this class, we don't really have that. All we have are just associations, and that's okay. We're okay with that. We're okay with just saying there are patterns that are existing, and we're going to try to detect those patterns. It's a good reminder the basic elements of our proposition in this course, the symbolic form is y in the little squiggly thing called a tilde x question mark. Is x associated with how y varies? Y in our case is going to be considered the dependent variable or a response variable. And that's the focus of our analysis, that usually the disposition and attitude, a belief, a behavior, maybe it's something that we could better understand through other possible values. Our independent or explanatory variables X. This helps try to explain these differences in Y, and these are usually the properties, the demographics or household characteristics that a researcher believes may account for the differences in Y. And this relationship is how you propose may explain these differences in Y overall. And quick reminder, I'm going to do a crash course of this. You want to set up your own null and alternative hypotheses, and these are just statistical statements about our population using our propositions. The null hypothesis is usually that there's no relationship. The idea of someone's innocent until proven guilty, which is the alternative or research hypothesis. And our research or alternative hypothesis is basically that there is an association, there is a relationship going on here. So with our analyses, we want to test between which one can we go for. We ideally want to have the alternative hypothesis. But if we can't, we have to just say there is enough evidence to reject it and set it with what is the null hypothesis. Now, bivariate statistics allow us to test our propositions. So y is that related to tilde x? And which bivariate statistics you use is dependent on the types of variables in your proposition. If they're both, numeric, because all these variables are going to either be numeric or categorical. If they're both numeric, we're going to do something called correlations, regression, module 7. If one is numeric and the other one's categorical, we'll use something like ANOVAs in module 6. And if both x and y are categorical, that will require another type of bivariate statistic or crosstabs. And eventually, we're going to talk about something called chi-square. So let's do some work ahead, just like before. We're going to go ahead and use that 2018 data set with gun control, using that and comparing it to degree level that we did in the rules of writing, that we did in the last lecture, and enhance it and make sure we're good to go. We have our symbolic form, gun control related to the education level, alternative hypothesis. We think these things are related. Why? You want to have a because statement. You don't have to say because exactly, but you need to be able to explain why you think those two things might be associated with each other. Give a reason, give a statistical opinion that are based on your own social science brilliance that you already have, that you had before you even took this class. But then we need to sort of give the counter argument. We have the null hypothesis. We got to be open to the possibility there's no relationship between X and Y. Stating the null hypothesis reinforces the researcher's objectivity and that they're letting the data speak for itself. We could be wrong, but we'll see what happens with the data and which direction should we be leaning toward. And so, for example, there's no difference based on education level with respect to America's position on gun control. That would be what the null hypothesis would essentially be. Again, we're going to provide this stuff in terms of a crosstabs. And we'll have y, the dependent variable, be in rows, while the independent variable, the explanatory variable, be in columns. And we'll make sure to put the percentage of the crosstab of the columns total. We're also going to look at some tests of significance to determine whether the findings are generalizable to the population. Tests of significance are often referred to as inferential statistics and can be explored through two different lenses. Module 4 talks about practical significance, and we'll expand on that a little bit today. And we're also going to talk about statistical significance. And this allows us to answer the question, how confident can we be the relationships that we are observing in our sample data reflect something broader and generalizable to the population? It's a huge question. Can we say that the stuff we got from GSS, it's a good enough survey? This actually represents all 307 million people in the US. We'll figure it out. So when we use Jamovi, we get something that looks like this. We go ahead and make our contingency tables. You did this in module 4 when you did the blog posts. And we get a table that kind of looks like this. We analyze this stuff already. We know how to do this. This isn't too bad. We're going to now be able to take this stuff and analyze practical significance versus statistical significance. In performing statistical analyses, we typically have both a practical viewpoint as well as a statsy viewpoint. The practical one has a look at the descriptive statistics and compare them to decipher whether meaningful differences exist, while the statistical significance viewpoint has us, but really Jamovi, to use mathematical statistics and complex procedures to determine whether these differences extend beyond reasonable doubt. Just, like we got an offbeat sample that year. When we have large data sets like the GSS, we typically require that we have statistical significance to exist. That is almost like the baseline. But it's usually not always good enough. With more data, sometimes the claims that differences exist are not necessarily because there are huge gaps and changes. We just have a large number of observations. And those differences we may not think are huge. And for that reason, we ideally want to have both statistical significance as well as practical significance and make sure that they go hand in hand to really make a conclusion about something. Quick run through the percent difference rule. I said if there's like between less than 8% points, I don't think there's a big relationship. There doesn't seem to be a lot of evidence of a relationship, so we can't reject the null hypothesis. But if I have slight to moderate relationship between 8 to 20 points of a difference between the highest and the lowest, we just look at sort of the two polarizing figures and see what the difference is, the big math we had to do. The slight, moderate, medium, strong, but strong relationships, it's definitely over 20 percentage points. Really strong or even robust. This really nice if we can get over 20 percentage points. There's a clear example that a relationship is present. So returning to our gun law example, 75.6% was the highest for bachelors. The lowest was less than high school. It was 68.4. And we wrote about this. We talked about this. We did this. And we basically said, those two differences, 7.2% difference, based on the percent difference rule, did not suggest that there's a relationship between education level and opinions and gun control. This was, what I said. 7.2%, 7.2% is less than 8%. Boom, not a lot of difference. We're now going to add something more. We're going to start talking about the visualizations and go beyond just the contingency table. When visualizing the categorical breakdowns for two or more variables, it's also useful to explore the various methods to display our data, as it helps us see whether a noticeable difference exists. In Module 3, we explored these graphs through bar graphs and bar plots. Module 2, we actually did graphs too, with box plots, histogram, density plots, and so on. But now as we jump onto two categorical variables, we're going to continue to work within our bar graph family. But now with two new ways to view these breakdowns through stacked bar graphs and side-by-side bar graphs. We can use a special kind of stacked bar graph, in fact, called the stacked 100% bar graph, which helps us spot practical associations easier if they exist. And we'll talk about that in a couple slides. To begin, a side-by-side bar graph will place the different groups next to each other to compare the values across the categories and from the x variable. This breakdown often helps us see how the joint events vary over possible combinations. So here, these are just in frequencies, and I can see that high school, for those who were in favor of the gun law, a lot of those were like, this is a huge number of individuals. It's the biggest number in this joint event of high school degree only and in favor of gun laws. This situation seems to be a noticeable gap, and that we get a lot of people who are surveyed who answer that way. I also but I also see there's a lot of people who are just in high school in general. A stacked bar graph can help break down these sort of groups and see that this is a major group. We get a lot of people who are surveyed who completed high school only, and then a bunch of other different ones. So the breakdown helps maybe to see distinctions among different column groups. But now I want to start to think like, are these numbers how they related to the whole? But also, does this kind of tell us, is there a relationship? I don't know. These two graphs have their purpose. They are useful. I don't know if they necessarily fit within the context of what we may be looking for. And I think this is the great alternative for that, and probably the most useful of the bunch. And so it's called a stacked 100% bar plot or 100% bar graph. Plot, graph, I'll use these things interchangeably. Feel comfortable with that. These plots combine the visual of a stacked bar plot and transforms it so that the bar heights represent the column percentages instead of the frequencies. And what I mean by that is before I had these at like sort of different heights because we were talking about the counts, and we just had a lot more high school people. But if I take it to percentages and basically rescale it, I can now start looking at these sort of column percentages we saw when we did the contingency table with doing column percentages only. Taking the percentages, this is a visual representation of our contingency table. So skim back to the contingency table, the percentages here. I basically take those and graph it. And as I told you all before, pictures are worth 1,000 words. A visual may often help make a better breakdown, evaluation of these practical differences and help others see things immediately without having to read that table. If no practical differences exist, or very little practical differences exist, these breakdowns, basically the splits in the color, will look pretty darn similar to each other, respective of each of the sort of x-axis categories. So with degrees versus gun law, we go ahead and we put like the gun law response variable here and the predictor explanatory variables here, these categories here. And I can see that there are differences. There's something there. I do see that these aren't exactly perfect, but I don't see huge differences. I don't see huge gaps. I don't see them looking extremely different from each other. And because I don't see them as extremely different from each other, I don't know if they're related or associated with each other. We already kind of know that. We did that with the percent difference rule. So I think that's not a big deal going forward. But let's say I use the degree being explained by the mobile 16 variable that we talked about in the workshop. If there is an association, if there's a relationship, we're going to see big differences in the breakdowns of each of these categories as we sit in different categories of the independent x variable. Here are all the breakdowns, the categories over that variable, that contingency table we used for degree in mobile 16. I don't need to be a statistician to see that the yellow rectangles look very different over these different bars. The middle one is the biggest. This one's quite smaller. In fact, it's almost 1.5 times larger. These are very different. This tells me, just from eyeballing it, there is an association, there is a relationship. And I bet I see the big difference in this sort of haze-to-curl background. And this backs up exactly what we said in our workshop when we talked about the writing up of this stuff. To summarize what we're going to do, if there's no major differences, we expect that each of them look similar. And so we report this as no relationship and supported by the similar breakdowns in our provided stacked bar plot. If there is a major difference, then we should see the major differences breakdowns and how each of these bars appear. And so we report this result as a relationship that is supported by the different breakdowns in our provided stacked bar plot. I won't go and say stacked 100% bar plot, and this is why. If you're going to provide the graph, you could put it in as like a caption, the stacked 100% bar plot of this material, but I'm doing the write-ups. If I say stacked bar plot and so on, I think that's enough that we need. It tells the reader that they can easily see from our graph that we provide that this is different. And yes, you could say stacked 100% bar plot. It just feels a little bit like overkill. They'll get the picture, literally, because you're going to provide the picture alongside of it. And remember, our goal as a researcher is also to explore where differences may occur. Sometimes it's useful to glance at the stacked 100% bar graph before performing the percent difference rule that may inform us which categories differ. So, for example, I want to check degree in Mobile 16. And in our workshop, I told you all to look at the high school one. Well, I don't know. What if I didn't? Where would you go? Which one would you check out? Here's where this graph actually does a lot of heavy lifting for us. As I said before, it's like, boom, wow. Over there, we clearly see that this 40%, the yellow, the 59.5, the 50.8%, these yellow rectangles are vastly different from each other. That one might be the one that I want to compare percentages across because I can probably detect that relationship pretty easily. So that might be a nice little hint to do that part first before you figure out which one do you want to establish differences through the percent difference rule. Now, for reporting the results, I'm going to go through this very quickly. But note, this is the exact same sort of write-up I provided when we talked about this during the workshop and the rules of writing and everything. The only thing that's different is this line that's in purple, where I say that after the percent difference rule, I basically add that this lack of a relationship is supported by similar breakdowns in a provided stacked bar plot. And it's basically reinforcing the visual that goes alongside our actual analyses. So, while these findings, does education level matter in explaining one's position on gun control? Americans with higher levels of education may be more likely to support stricter gun control measures because they have read more on reports regarding gun violence. Comparing percentages shows that those in favor of gun control laws are highest among those with a bachelor's degree at 75.6%, comparison who finished less than high school at 68.4%. This 7.2% difference based on the percent difference rule does not suggest that there's a relationship between education level and opinions on gun control, and this lack of relationship is supported by the similar breakdowns in a provided stacked bar plot. While these findings report on 2018 data, it actually would be interesting to look at the relationship at a present time, given how we depict gun control and gun use in our country. Furthermore, it may be interesting to explore whether certain specific restrictions may be endorsed more than outright bans. Big bunch of review, lots of material we covered. Take a break. Once you get done, take a breather, try some of the practice questions, prepare you for the quiz, and we'll get started in the next piece. All right, you ready? Let's start testing for significance. Now let's talk about testing for statistical significance. As just said before, this is all just a refresher. Performing statistical analysis, we want to do a practical viewpoint as well as a statistical viewpoint. Practical viewpoint we just covered. Statistical viewpoint are going to use Jamovi and get a little bit, more into the muck and mud of things and test for that statistical significance as well. So practical significance should feel more like review from our previous module, and maybe a little more formal. But now we want to see if we have statistical significance. We're going to ask, are these differences actually there in the population? Or could have randomness, the way that we got our sample, just been the culprit? Overall, it compares with all cells that we'll look at and try to use complex mathematical formulas related to the normal distribution we mentioned very briefly back a few modules ago, whether there's a chance that luck is relatively low. And these things called eventually chi-square and F we'll be covering over the next few modules. The chi-square, written as, so it looks like a curly X, which is really the Greek symbol chi squared. Or if you want to just put CHI-SQ for chi-square, I think that's awesome. Do that. I'm totally okay with that because I want to make sure that you write something that feels like in your own language, at least for right now, but definitely comes from your own words. It's a test of statistical significance that subsequently should only be used when working with data that's representative of a population that's under investigation. Chi-square is a test of significance that we use when working with crosstab data. And when we're working with categorical data and testing the relationship between these variables, we can use the chi-square test to determine whether or not we can be statistically comfortable in generalizing the findings we observed in the crosstab the population as a whole. The chi-square formula is this weird math thing where we say observed minus expected, or square that divided by the expected, sum them all up. And you know what? Blah, 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 blah. Nobody cares. I care. Statsy folks may care. And that's useful, honestly. I think it's really great and very important, but not vital for this course. At least the formula crunching out the number stuff. Because honestly, if I'm going to be very, very blunt with you all, even the folks who are on the very statsy side, we may have to do a few things here and there or number crunching to prove our worth in classes, but we're going to be doing the same stuff you're doing. We're going to put it into some sort of computer programming system and let that do the number crunching and analyses. Because to be very honest, doing all this stuff by hand is a waste of our time. It's important to know where it comes from, have a historical element, and see where these things are actually being drawn. But it's not important to do all this stuff on your own. In fact, what's more important is that you can use Jamovi to let it do the number crunching and then make you interpret the stuff more correctly. And that's the more important part. So now we just have to learn how to set up our chi-square test and then how to interpret our results. This requires that we talk about setting our significant levels. And this is a quick detour that we got to get through. I'm going to tell you all, your brain's going to melt a little bit. If you need to take a breather right now, please do. Get ready to buckle up. We're going to head to the rodeo. And when using our test of significance, before using chi-square even, we need to set this level of significance so that we can determine whether or not we can reject our null hypothesis, reject that there's no relationship, in favor of there being a relationship, determining whether a relationship between two variables are statistically significant. Statistical significance in general, it's the error rate that we're okay with. Being wrong and claiming there's a relationship when in fact we screwed up. There isn't. We didn't do anything wrong per se. We just got unlucky. And we got a bad sample that isn't really the best representation. So it told us we had relationships, when in fact we didn't. It's like 8th grade relationships. We think it's a relationship, but it wasn't. These levels of error rates that we could be okay with, the significant levels, can range from 0 to 1 or 0% to 100%. But we typically want low values because we don't want to be wrong often. These lower values allow us to have stronger confidence. And we'll talk about confidence a little bit when we get into module 6, because they're actually very, very closely related. But these lower values allow me to have stronger confidence in the conclusions about association. And to be honest, there's no magical significance level. I want low ones. We ideally want as low as we feel comfortable with. But there's nothing magical about these values. There's nothing. We might see things that are very similar. 3 significance levels that researchers often use are like 10%, the 5%, and 1%. And 5% is the most often seen in statistical tests. It's the one that I think is most important for you all to like grasp on because it's used a lot in conversations of what is significant or not. It doesn't necessarily mean that. I can go into some rambling and ranting, and other statisticians have rambled and ranted that really maybe it should be smaller, maybe it should be half or even more so, because 5% is a pretty high error rate still. And it's kind of inflated our idea of what are significant results. But we're not going to stress about that. Not in this class. We're going to actually stay chill because I want to get you all used to this stuff. I want to get you all to the point where you are comfortable with some analyses. So we're going to use the ones that are like most common among researchers so you can gain the lingo to get comfortable. But no matter what you end up choosing for your own personal preferences, you never try to test at the 0% significance level. This virtually leads to never concluding you have a relationship or statistical significance. The reason being is that because we're getting a sample instead of a population, we're going to have some error in it. Hopefully it's small. We don't want to make it a big difference, but we'll have some error in it. And since there is some error is bigger than zero, so we'd never be good enough. So we'll want our error level to be low, but zero doesn't really work here. And when evaluating our data, our level of significance will then be compared to something called a p-value for our test. Now, I just mentioned performing our test, statistical significance, we're going to have something called p-value, the probability level. This value is used to test what are the chances of incorrectly concluding that two variables are associated with each other based on the data we sampled. Just like the sig level, it's going to be between 0 and 1. And there is a connection beyond that. The p-value is what we're going to compare to our significance level. See the image below. The p-value is less than, smaller than, or equal to our significance level. We think we have enough statistical evidence. It means that the error that the p-value says it is lower than what we are. It's better. Lower is better in this case. It's lower, it's better than what we're comfortable with. So we feel good with rejecting and claiming there's a relationship, there's evidence. But if it's greater than our significance level, in this case, higher is worse, higher is bad. If it's beyond our significance level, we don't really have enough statistical evidence. And we say that we fail to reject our null hypothesis. And the following are three typical values, as we talked before. 5% significance level is basically if no relationship actually existed. We may be unlucky about 5% of the time with our data collection and gotten a sample that makes us incorrectly conclude that a relationship exists. In a courtroom analogy of that innocent and guilty thing we talked about before, that's like concluding in a trial that we collect evidence that wrongly convicts an innocent person 5% of the time. That is the risk we're going to run by not getting the whole population. It's not typically possible to get all 370 million people. We don't have the time and money for it. A sample, usually we can get a good enough sample to make it worth our while, but we do have some risk, and we say this is the risk level we're going to be okay with. Our goal for statistical significance is then going to be getting a p-value that's less than or equal to 0.05. At the 1% significance level, there's less of a chance of making an error compared to the 5% significance level. This is like we only be wrong at most 1% of the time if we conclude a relationship when in fact it isn't. There is a bigger chance, though, to fail to detect or miss that relationship that actually exists. So be careful about that. Goals for statistical significance, getting a p-value less than or equal to 0.01. The 10% significance level, 0.10, kind of on the opposite end. Greater chance of making this error compared to a 5% significance level. We may accidentally send more guilty people to prison. But there is a smaller chance of failing to detect missing that relationship that actually exists. The goal of that statistical significance is getting a p-value less than 0.10. Take a breather, folks. I want you to screenshot this slide and frame it, make it your best friend. Because in this class, I'm not going to go all over the world with this stuff. I'm going to have you all focus on 5% significant levels only. Is it because it's the best one? No. But I think it's the lingo that's going to be most common in the literature you're going to see in your research courses, in other sort of publications and stuff. So it's the thing that I want you all most comfortable with. If you want to explore those things and have some like critical thought points at the 1%, 10%, even 0.5%, that's cool. I like that idea and get comfortable with those things because that's valid too. But we're going to focus on these relationships to build your foundation. In another class, in another research course, you may explore it through different things. But if you can get it here, then the step up will feel like less of a hurdle and more like one of those stepping machines in the gym. And so the goal for statistical significance is to get a p-value less than or equal to 0.05. If it's less than or equal to 0.05, we have a relationship. If p is greater than 0.05, no relationship was found, or we don't have evidence of a relationship. Deep breaths. How's your brain doing? Melting? Do you need to make it solidify a little bit, put it in the fridge? Totally fair. We'll try and practice an example to contextualize this stuff. Take a breather, let your anxieties ease out. And as a reminder, and this is one point that like when you're reading a book and sometimes you sneak to the back to see the ending. I'm going to recommend for anybody who's feeling a little bit overwhelmed, go ahead and take a sneak peek into the rules of writing worksheet and the additional problem and actually see the additional part that I added in there compared to what we did in module 4. Because you're going to see like, oh, just like just like in the workshops when I showed you all in module 4, and you're like, is that it? I'm like, yep. And you're like, oh my goodness. Same idea here. We're going to spend this entire lecture. There's a lot of material. And to be honest, there's a lot of concepts. So I don't want to like diminish the impact of why I'm talking about all these things because it is important to understand it. But it's only going to lead us to a few extra lines of what we've already done, which is kind of nice. We're not doing a lot extra in terms of writing. The stuff that builds to that is kind of huge. So we'll continue to look at 2018 and say, would you favor or oppose a law would permit a person to obtain a police report permit before he or she could buy a gun? So we'll sort of set up our propositions, do this before. Does education level matter in explaining one's position on gun control? And blah, 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 blah. We've done this before. I'm going to skip over pretty much step 1, symbolic form, 2, your alternative hypothesis, 3, your null hypothesis. We talked about all these things. We're now going to go into step 4, setting your levels of significance. We're going to start at the 5% level of significance, which means you will be using a p-value and comparing it to a value of 0.05 to determine whether your proposition is statistically significant. So what statistical tests to use? They're both categorical variables. So we're going to use a crosstab and a chi-square to test the relationships. Make sure to check the Jamovi short video. Whenever you're doing these contingency tables, this chi-square thing should already be in there. It should already be part of the stuff. But if it's not, all you have to do is check this test and you're good to go. Get a table that looks like this. Nothing new. You did this in module 4. What we do get is new is the chi-square analysis. This little table that usually goes underneath it. So how do I interpret these results? There's going to be 3 values you want to read when interpreting your chi-square results. The first one is talking about just the value itself. It's using that sort of chi-square, x squared, or ch dash sq. All those things are fine. Having the 6.04 is just stating the sort of value that the computational stuff comes through. The next part is what this DF thing called degrees of freedom. And I don't worry about that too much in terms of like having to do a lot of analysis of it. It's really just sort of a proxy measure, sort of a way to talk about how big your table is, like how many columns, how many rows. And the bigger the degrees of freedom, the bigger your table would be. The p-value then is the last part, and this is the most important part. It reports the box for making our decision. P-value tells us the probability the relationship can't be given over chance occurrences brought on by who was sampled the GSS and subsequently the statistically significant. So in our example, we want to put in parentheses, chi-square is equal to 6.04, comma, degrees of freedom is 4, p-value 0.196, and be really difficult, bust out a calculator, 0.96 compared to 0.05. It's 19.6% bigger than 5%. Yes. Yeah. Because it's bigger than 5%, even bigger than 0.10, this relationship doesn't seem to be statistically significant. It's too big, at least at the 5% significance level. Now, sometimes I'm going to get a p-value that's actually going to look like this. This value less than 0.001. What that is telling us is that the p-value is really small. Super small, that really anything that we like want to test at any significance level is going to be considered to be, this is going to be smaller than that. And so we can easily conclude that we have a statistically significant relationship existing here. So how do I go ahead and put both the practical and the statistical significance combined for our analyses? I'm going to be honest with you all. I'm lazy. I'm not going to go ahead and read this entire thing again because I've done it too many times. I'm just over it. I'm over it. I talked about it in module 4 in the lecture. We went over in the workshop and we talked, and I did the little song and dance on the rules of writing. I even went over this thing before, at least all the stuff in black and even the stuff in purple, when I talked about practical relationships at the beginning of this lecture. Only thing, and I told you all, if you're feeling anxious, go ahead and check the rules of writing and see what's being added. I spent an entire lecture to get us roughly 2.5 lines to add to our stuff. Now you're like, Professor Sparks, why did you do that to us? What's wrong? Why are you like that? I'll give you the reasons. But in this case, those 2 lines are so important. As a good reminder, the beginning and ending is really just your opinions on things. And the middle is where the stats really become statsy. We talked about and sort of eased into things with the difference rule, percent difference rule. And that's important. But now when I add the purple part, I'm giving a visual that also reinforces the practical differences suggested by our percent difference rule that we saw. Furthermore, I am going to also conclude in this red line that there is statistical significance. And note that this format is important. I would say a lot of people who don't follow this format or got something that looks different probably got it from generative AI, ChatGPT, Gemini, something like that. And that's how they fail assignments. Very, very aware that this is the way we talk about these things in this class. You may do it differently in another course, and that's fine, whatever. I'm not bothered, but you need to write it out this way because this is also you all telling me you know what these things are. That's you proving to me that you know what this stuff is. And so the stuff in red also has another purpose. It's telling anybody who is anything into stats, either a statistician or a high-level social scientist who has done a lot of stats, that you did your homework. You did the work that goes beyond just some percent difference rule, better than just some eyeballing thing, and has approached it from a very formal, very professional statistical significance mindset. And so that's important to also provide this, add this to the mix. It strengthens your argument. And just like a quote from in a history, psychology, social work paper, and so on, this stuff in parentheses is basically citing your work. This is your in-text citation to explain why you think these things are statistically significant. So it's super vital, super handy, and actually not that hard to add into it. Always remember, in your direction of future research, you should be good to go. Remember, as always, review the rules of writing and make sure you check up on the two new things that we have. It's a little deceptive. The first page looks exactly like Module 4. It's intended to, so you don't have to necessarily look at Module 4 anymore in terms of the rules of writing. You can go right into Module 5, and it has everything that you need from those two modules. But they also, on the second page, is where the stuff becomes new as a good reminder. Writing up your chi-square results and then writing up your stacked 100% bar plots. And the things you're supposed to add into your writing to enhance to the next step. It's a good reminder also, go make sure you watch the Jamovi videos, follow the worksheet that goes the step-by-step things that goes alongside the video to help you get good to go as you start to do these things. Create the example for problem 0 and do your homework and blog posts and so on. Short break, try these examples, get comfortable with this stuff, and feel pretty good about yourself. You did a lot of huge concepts that I think overall is very, very, very tricky. Take kind of a little bit of pride in yourselves. You're really starting to jump up to being like that social scientist that sounds very formal and professional. As you do these examples, which also should feel pretty chill, at least in terms of the blog post. The homework's going to be new. But it's not a lot of extra work. It's just a lot of extra, like, getting those things to make sense in your brain, which I'm glad to be able to do for you all. But if you're having more questions, come to office hours, shoot me a line, help out, and good luck. As we jump into, other questions of like, what happens if I want one of my categorical variables to be numerical instead? What do I get to do? Then we jump into module 6, and we'll talk about that later. Have a good module, folks.